Well, thanks for everyone joining the SED3 seminar today. It's a special seminar. We have a guest from Japan. We have uh, Hiroku
Hi.
and also Sho. Yeah, thank you for visiting Seattle. And it's a project funded by Amazon that we try to have a international partnership between University of Washington and University of Tsukuba, funded by Amazon for this sleep disorder diagnosis project. And in particular, we want to utilize the real-time AI and also the cutting-edge AI model algorithm
Yes.
development at UW with the leading sleep research institute in Japan in collaboration for pushing the frontier of sleep diagnosis. So this will be a 4-day event. It's actually composed of a seminar talk between Washington and Tsukuba, also the lab tour that for our Japanese guest. And so we'll start with Dr. Hao Fan on the closed loop BCI development at Washington. Then we will start the 4-day event, but we'll take a break actually because most of the time we will bring our Japanese visitors to see the lab and also the campus research environment at UW. And we will resume the seminar at 3 p.m. In the room here and also in the Zoom, and allow our collaborator connecting from Japan. So welcome to stay with us and also watch our development for future. And we will have another bigger workshop in March 2026. All right. So,
Right. Yeah.
Hao Fan, and could you briefly introduce yourself first before you start? Okay.
Yeah, sure. Hi everyone. Good morning. So my name is Hao Fan. So right now I'm like co-advised by Adi Schritzman and Amy Osborne, and I was affiliated to this A3D3 Institute. And today I'm very glad to present some of my recent work in doing closed-loop BCI. And please ask me any question during the seminar, and I'm free to take any questions. We can get started. So today, I think my topic will be closed-loop BCI for the treatment of brain disease and disorders. So today, I will try to summarize most of the work into the 4 part. And we start from a very high-level introduction of what's the brain-computer interfaces. And after that, there's another important part, which is the brain decoding, which I will explain a little bit, but it's the most important part. And I will ascribe this one to the afternoon session by I think it's not Dr. Chanley right now. He is a PhD candidate, but he will get his PhD pretty soon. I think just in a few months. So afternoon session will be mainly based on the brain decoding. And today my main topic will be the robust adaptive brain-computer interface for treating brain disease and disorders, which is my title. And after that, I will have a short discussion and questions, and also take any kind of after seminars Q&A. So we can start with this kind of brief introduction, and I would like to ascribe this BCI into 2 parts. So first part is called brain decoding, which I would like to say in a plain words like read from the brain. And here are 2 examples about what kind of brain decoding means. So usually based on the recording device, we usually would categorize them into like 2 categories. So one is like intracortical BCI, which we have some implanted device into the brain, and we will do the recording. And at the same time, we will ask the subject, it can be the monkey or like a human, to do some kind of either the behavioral task or the cognitive task. And then we have a kind of like a pair of the input and output, and we can build some kind of models, try to understand, try to predict, try to like do the classification about how can we infer what's the kind of knowledge we can get from the brain signal. And the other part, which I think right now is quite widespread, both in the academia and the industry, by using the non-invasive BCI, for example, like the EEG. I think some of you guys are pretty familiar with the EEG, which I think is more safe, and it has kind of like whole brain recording. And I think the task is almost the same, like they ask the subject or the patient to do some kind of task, and we can record the EEG signal, which is another kind of brain signal, and we do this kind of recording. For example, here is a example that I draw. Basically, is we can try to decode the human's mood state or like emotion state via this kind of EEG recording. Yeah, so this part, I think it's more about like a machine learning based, and most of this part, so you guys will see more in the afternoon section in Chance like a presentation about how can we decode this one efficiently, and how can we decode it precisely. So this is the first part, which we say like record from the brain, read from the brain. And the second part, which is my main topic, is write to the brain. And here the technique people usually call it neurotechnology, brain stimulation, bunch of methods. And how it usually works is, I would like to approach it as kind of how can we write to the brain, how can we control the brain. And the motivation from it is right now, many people in this world, they are suffering from neurological and neuropsychiatric disorders. For example, like epilepsy, Parkinson's disease, depression. And recently, according to our global health matrices, I think in recent Lancet publications, this kind of brain disease actually causes a very heavy economic burden, and it's very prevalent, which means how can we deal with this kind of disease, especially at the time when the drug treatment, the traditional drug treatment, is not that effective. And luckily, I think over the recent decades, not recent decades, I think just over the past decade, the neuromodulation technology is kind of very promising a strategy that try to treat the brain disease via a very simple diagram, which is we have implanted device. You can see here, maybe it's not that very clear. So I think this is the device that I copy paste from the MetroLink, which is a very widespread, wider and famous company in United States doing the neurotechnology. Neurotechnology, and how it works is very simple. Basically, is we have this device, and it will create some kind of a pulse trend. It's kind of like a very regular with a particular or predefined amplitude, frequency, and the phase. So it will generate this brain stimulation, and the target is some kind of particular brain region. For example, there are some kind of pre-analysis, clinical analysis where the brain disease usually would happen in some kind of brain area. So for example, like in Parkinson's disease, it should be a basal ganglia area. But in general, this is just a very simple treatment. So we will send the brain stimulation to a particular region, and we hope this kind of brain disease and the kind of the symptoms can be released. So that brings us the main topic in our like a recent BCI development, which I would like to call it like the next generation of BCI, which we usually have two parts. Separately, read from brain and write to the brain. But right now we can somehow, it's some kind of like stage we can try to incorporate them into a full system, and we call it a closed loop BCI. And to develop the closed loop BCI, we will use a lot of like interdisciplinary knowledges from the system to control theory. How can we model the brain? Some neuroscience ideas, neuroscience understandings about where the disease, where the signals comes from, and what's the target brain regions. And we will also use some machine learning, for example, like how can we understand the brain signal in a very precise manner. And it has a very wide usage for treating brain disease and some kind of scientific discovery. So, yeah, so our main purpose today is about the second part, which is right to the brain, which is more close to the future collaboration with how can we treat the brain disease, right? How can we treat for example, the sleep disorder is some kind of disease if we can explicitly formulate it. But I developed this algorithm and this theory from very high level. And we start from this one, which we already saw, and I would call it like an open loop brain stimulation, which you can see is very simple. It's very straightforward. And the straightforward, well, borrow something not very good. I can say it's very naive design, and it will cause uncontrolled symptom variations. And I think that based on some clinical results, this kind of method has been applied to some kind of clinical trials, and the efficacy is still variable. So as the next step, people can think about it is try to close the loop. So one way to close the loop is basically says, can we understand the brain signal after we do the brain stimulation? So for example, we can combine the brain decoding, which we can have some brain network connectivity, and by using some kind of neuroscience ideas, we can try to define. And I know it's very hard, but we can try to define. Assume we can try to define a neurobiomarker, and this biomarker can somehow indicate the disease symptom. And once we have this disease symptom indication, then we can build a very simple on-off controller or very simple like brain stimulation methods based on the value. And we can automatically turn it on and turn it off just based on its real-time values. And that one build our first prototype closed loop BCI system. And here is a very simple diagram. However, this kind of setup, first, I can say this setup has already been tested in some of recent clinical trials, and it works definitely pretty well compared to the open loop design. However, if we think about this kind of whole design from traditional like a systems control theory perspective, this one is very heuristic, which means it's model-less, it's on-off control, and still the efficacy can be improved. So work from here, which is almost like most of my important contribution in this kind of field is, can we consider some mathematical modeling, some dynamical modeling of the brain network and try to build a closed loop system based on some kind of well-established and stability or robustness guaranteed control theory. Then the question moved to how can we model the brain dynamics based on our previous decoding results. So the first question we need to answer is when we say the model, what do we need to model? So right. So when we say to model, I think here the answer is very simple because we focus more on the disease treatment. So we want to model the brain output to the stimulation input, which can So this is like a simple diagram. So which can motivate us, we need to build an IO model structure. And we are very lucky, like people has been well established the modern control theory. For example, the dynamical linear state-space model. Also, people who are familiar with the state-space model should be familiar with this one. So we can just define, right? We redefine what's this XT, YT, and UT in the modern control theory. So we would say the UT is our stimulation input, which is some kind of potential therapies that we will give to our brain. And as a YT is our neural activity. And the relationship between the UT and the YT can be recursively written via latent space XT. We usually call this XT as a brain state. And by building this model, then we can also we have some kind of random noise, Gaussian noise to make the model to be a stochastic model to make it more robust. So we're starting from this model, and once we have this model, the next step is try to fit the model parameters, which I think in modern control theory they have a very well established method called system identification to model the to giving the recording data, right? Giving the input output pair, we can try to model the brain this kind of equations and try to model the brain dynamics. So once we have these models, then basically is we can try to build our control on top of it. And the way to build our control, we can also borrow the idea from control theory, which we can apply a common filter. The common filter can help us estimate the brain state. And once we have the brand state, we can try to build a linear controller, for example, the linear quadratic regulator, to regulate the output to some kind of like a desired or like a target trajectory. So for example, here I give a concrete example. Here is a very a clear illustration, which let me explain a little bit. So in this case, is we try to regulate the mood symptoms of the brain, which we define the mood level as a kind of zero level, and we're starting from some kind of unhappy or depressed state, and we try to make it to be like to be the healthy state or like a healthy mood state. And what we need to do is we need to develop this linear controller, and because this linear controller is based on what we estimate in real time about the common filter and our desired output, and you can see at around like time 60, the controller start to work, and it tries to changes the stimulation pulse trend, and it gradually drives the depression state to a healthy state, and it can after drive to the healthy state, and it's the stimulation pulse trend is still changing over time, right? Still changing over time, try to stabilize it, and that way gives a very simple illustration and a very straight illustration about how can we do this kind of closed loop control for typical like brain disease. However, if we stop from here, people will say, "Oh, then what's your contribution?" Right? So it seems like the contribution is you translate, well established the theory, like the modern control theory, to the BCI field, and what's your true contribution. And I want to say, like, my main contribution is we started to consider something more practical, which means in the prior controller design, you can see it's very naive. Because why it's very naive? Because we assume the underlying brand dynamics is nonlinear, which I write it as like equal. However, the brand dynamics we know is, I can say, is the most complicated dynamics that people has been met in real physical systems. And usually I would like to approach it as a very general function, like it's a measurable function, control and the function includes the the controller input, time, and like some kind of noises and some kind of unknown uncertainties. And in general, it's nonlinear, non-stationary, and full of like system disturbances. So if we consider the underlying dynamics as something so complicated, and if we just use our simple controller to build this closed loop system, here's a very straightforward illustration, which means if we don't consider those nonlinearities in brand dynamics, you can see this kind of brand controller, this kind of control performance behaviors called, I can say it not that good, right? Previously, we can stabilize at the target level, but right now we have some kind of steady state control error and still have some kind of variations. So basically, then it motivates the most important work in my past research is we need to consider the nonlinear modeling and try to construct a robust adaptive BCI controller. And to do that, we follow the model-based design, and we start from this simple model, which we are being described, a dynamic I/O model. And what we need to do basically is we try to add some kind of uncertainties in our modeling, and we by some kind of mathematical separation, we usually call it try to separate it into some range space and non-space. And in the range space, we have some kind of delta omega ut and G1 xt. We would like to refer this to as some kind of time varying system filtering gain, synaptic filtering gain, and some kind of unknown control input. And this one, yeah, we will refer to some kind of more complicated dynamics. And those kind of whole things is unknown prior in our underlying model fitting, which means we assume some kind of uncertainties that happens in real time, which we need to address them when we try to build our closed loop therapies. And because right now we change our model, then in our BCI controller design to closed loop, we right now need to have another kind of component. We call it like robust adaptive T, which is the bottom part that we need to design. Yeah, and then because of this separation theory, there's uh, underlying take home or the underlying functions of two parts is very simple right now. So one part is try to cancel the range space uncertainty, and the other part is try to cancel the non-space uncertainty. If we can cancel both of them, then we can achieve a very good like a therapy or control performance because right now there's no uncertainty terms, then the control performance should go back to the prior like linear control performance. Yeah, so we built this model. So the first way is try to see, okay, whether you claim you build a nonlinear model, but whether this nonlinear model really helps. So in order to illustrate that, we try to do a kind of I can say like a comparison study, which we compare our nonlinear model with the linear model on a kind of very typical Parkinson's disease. Is a very typical brain disease network, and we use this kind of same model, and we apply the like a modeling part to apply the same modeling, which means we control the same input and output and try to see different kind of modeling framework. And you can see with this model, with this nonlinear model, it really fits this kind of prediction trees very well. However, the offline model is a linear model because it sacrifices nonlinear availability. So you can see around like a time at 3, there's some kind of very large prediction gap. And in general, if we compare both of them, you can see it's very significant that our nonlinear methods can predict it very well compared with I can say the state of the art linear model. So this is the first part. We illustrated this. Okay, this nonlinear model really can work, and then we need to build our controller because we have this nonlinear model. Then to build the controller, we can just follow what's the standard way to build it, and usually we will, because right now we have uncertainties, right? We have 3 terms within this kind of dashed blue box. So we need to do first because we need to. So the goal of control is try to cancel these uncertainties. So what we need to do is we need to estimate them. Once we know them, we can safely cancel it. So we will first build an adaptive estimator, recursive adaptive estimator in real time. And then because of this whole system is a real physical system, so we further apply our low pass filter on top of what we have been estimated, then we can improve the whole system robustness. It's a technical part about how we derive this kind of things is a little bit nasty. So here I will just say like from the high level, how can we do what's the essential part within this robust adaptive part in this bottom blue box. And yeah, if you guys are interested, we can say more about it. And all the technical details is in the published papers. So right now we have built this controller design, and then what we need to do basically is we need to validate these kind of things before we apply to any kind of real applications. So the first validation is basically purely based on the simulation, and in this simulation, because thanks to the wider widely power, very strong power of deep neural networks. So we first use the deep neural networks as our brain, so we can simulate the brain dynamics. We can simulate the nonlinear brain dynamics. And we apply our controller and we compare this one with several kind of state-of-the-art algorithms. And you can see that across a very wide range of the deep neural network, basically we can try to control the nonlinear level of our system, how nonlinear our brain is, and we can see across a very wide range our proposed robust adaptive controller, which is I think is the bottom part. It achieves a very small control error, and it increases the stability. Even the nonlinear uncertainty is very large, and it also maintains very good system stability and system robustness. Even the uncertainty level is very strong. However, if we only consider the very naive the open loop methods and the prior like linear quadratic controller methods and the performance for these three category performance is not that desirable. So that one gives us first confidence that okay, our model, our closed loop design can really helpful, seems very promising. And the next step basically is we next validate our algorithm on computational models, and this computational model is built is borrowed from a series of differential equations, try to describe the major depressive disorder in brain disease. And it's a little bit complicated, but in general, it's a neural mass model, and we can borrow this model as our underlying brain network, and you can see it's quite nonlinear. And in this case, we also try to test our algorithm with some kind of previous open loop methods and the on-off controller. And you can see if we use the open loop, right now our control target is some kind of brain signals. We want to stabilize it. And right now it also has some kind of stairs changing because open loop is kind of blinded, right? So it cannot check any kind of target switching in real time. So and also performs very bad, consistently bad. And the state of the art method, which has been tried in clinical trials, is this on-off controller, which we saw before. And you can see it performs a little bit good, which is it can try to react to some kind of target changing because the target changes, then the on-off controller changes. But you can see still has some kind of control error because of this because this model-less, this doesn't know the underlying brain dynamics. So if we apply our methods, you can see it can try to catch this kind of changing targets in a very good manner, and it greatly outperforms the prior two methods. Yeah, so that gives us a very good confidence about in the future when we try to apply the closed loop design to treat some kind of brain disease, we can try to apply the kind of nonlinear methods, try to conquer and try to do very stable and robust control. And the other thing that I want to say about this work is because our work is built on top of the control theory, so different from some kind of deep learning methods. These methods also has a very strong mathematical guarantees and the derivations for this kind of treatment algorithm development. Yeah, so almost there. So let me summarize a little bit about what I've been done here in this project. So basically, we're starting from a linear I/O model and a closed loop controller, linear closed loop controller, and because of we consider a more practical case in the nonlinear control system, nonlinear brain system to treat the brain disease. So we extend the linear model to include nonlinear uncertainties. Because right now we have these nonlinear models, then we can construct the robust adaptive BCI systems correspondingly. And then we build this full closed loop system. And with this full closed loop system, basically we controller, we illustrate this system, we illustrate the controller, illustrate the nonlinear models on first on some kind of simulated system, and the second is with evaluate on some kind of biophysically plausible systems, and both of the systems works very well, which paves the future for the future clinical potential clinical trials to apply these kind of methods. And that yeah, that's almost my presentation today, and I'm free to take any questions. Yeah. Yeah. Any question? Any question?
brain brain disorder, for example, depression.
Yes, so brain disorder, there are many brain disorders from Parkinson's, which is quite known that it's keep wiggling, right? And some kind of epilepsy. Yeah, so there are a lot of brain disorders right now in this field, and I think there are many ways that people try to build a closed loop BCI. Honestly speaking, I don't know how people think about it from what I'm thinking, and I think the closed loop system, when people say the closed loop system, people usually try to do something therapeutic. Yeah, but that's not the main case. But in terms of the more practical case, it's about the therapeutic treatment using the closed loop BCI, right? Because you can see, you can react to what you can detect it, then you can try to do some kind of treatment. Yeah, but I think some people are not doing something like this because they try to focus more like let me see whether we can go back. Let's see. Let's see, go to the very beginning. Yeah, so I can say the next generation of BCI. So one is for the treatment, right? For the treatment of brain disease and dysfunctions. And the other part is people build a closed loop system, they can further develop their kind of neural understandings because right now you have a closed loop system. Closed loop means I can understand what I inject to this system, and that gives me a causal, more like a causal understanding of this, how the system evolves. Otherwise, is I give something and you observe something. That's not about causal, it's about a correlation, right? But this closed loop can give you more like a direct evidence about how the system looks like because I direct give it. If I don't give it, then how it looks like. Yeah, yeah,
I think in sleep disorder,
yeah,
nightmare disorder,
yeah,
like or PTSD,
yeah. PTSD. Yeah, yeah,
it
yeah.
is very effective.
Yeah, very effective. Yeah, yeah. Yeah, so what I did here is kind of like a theoretical framework. So it's not specifically or exclusively for any brain disorder. It's in general a framework, and this framework definitely needed to be adapted to a particular brain disease. For example, in some of my publications, I illustrated on Parkinson's disease. I illustrated on depression, but I'm very glad to see how my algorithm can be applied to more area. And yeah, but what we need to do is we need to define. We first need to collect the data. Second is we need to define what's our therapeutic state, right? For example, in brain disease, is the rating is the like a subject rating,
Okay.
or we can have some even better target like can we based on just based on the neural signals. If we can based on neural signal, it would be even better because the neural signal is more dense, which means we can realize the therapeutic treatment in a more continuous way, right? If you based on the rating, then you can ask the subject to rate in the midnight, right? You should usually like just every day, right? Otherwise, the subject, right? So that would be more about like a discrete control, but this one is more smooth, more continuous control. But in terms of control theory, doesn't matter. It's just based on what kind of time scales that we can try to apply to. Yeah. Um,
Can I ask a question?
sure, sure.
Okay. Oh, thank you for a nice talk. I'm Keita Kawai I'm from Japan, but now I'm living in Germany. And Hiroko introduced me the URL today. Yes, thank you for nice talk. And I'm very interested in your research. And first of all, I'd like to ask the device that you use more. So can you show me the picture of the device again? Yeah. So I think this is the image of this device, and the left below one, it seems like the device was put into the inside of the shoulder or
Yeah,
chest
chest.
or
Yeah, chest is
chest.
inside of the chest. Yeah.
Oh, so that means you need like do the surgery to put into the device inside the body.
Yes, yes. So
Uh-huh.
people usually call it as a kind of implanted device. Yeah,
Mm-hmm.
implanted device. So we will have implanted device into your chest, which this one serves as a kind of like a you can treat it like a battery. Basically, it's like a battery, and
Mm-hmm.
it have two cables. and two cables. So one cable is for the recording, and the other cable is for the stimulation. But recently, I think last week there's a IEEE NER, like neuroengineering in this field, and I saw some kind of companies right now they develop something very advanced stimulation technology, which means that they can do this recording and stimulation within one cable. Yes, but this
Okay.
kind of things, I'm not very sure about how impractical people has been used because it really requires, like in United States, it really requires a very strict IRB, and you need to go with some kind of
Yeah.
surgery. So, yeah,
Yeah, I think the like FDA or ethical committee in the United States are very strict to put the like implant something device inside of the bodies.
yes,
So yeah, I'm just curious about that. And also this cable is also inside of the body.
yes,
Okay.
yes.
Yeah.
Yeah, so that makes like everything. So that one actually, I don't think that one is very smart, but I think the way people design about this one is
Mm-hmm.
try to somehow like try to decrease, okay, try to minimize the kind of noise, like the
Yeah.
recording noise. Try their best to cancel the noise, because if you have some kind of for example, like you have some kind of something on your back, right? That
Mm-hmm.
one
Yeah.
causes a lot of, I mean, every time when you like do some movement, that will cause some kind of movement disturbances in the like
Mm-hmm.
distant recording. Yeah, and
Yeah.
the stimulation.
So
Yeah.
So that now it's the device is on the process of the developing a new model or like a mini mimes and decrease the side effect of the brain, isn't it?
Yes. Yes.
Okay.
And
Mm-hmm.
right now, I see these kind of cables. I think both China, United States, and some kind of, I think mostly in China, I talked to some people. I think their kind of cables, they make it a very small, but I'm not a hardware guy, so but I can see it's very,
Mm-hmm.
very small. So
Yeah.
yeah, like a very like a, I can say like very thin, very
Like
soft, something
thin
like
and
this.
tiny. Yeah.
Yeah, thin, tiny. Yeah.
Mm-hmm. Okay. Thank you. And could you show me the slide of the like a deflection plane? You
Depression.
mentioned
Sure.
the yeah. Uh,
You mean this one?
oh yeah, this one. This
Yeah,
one.
yeah.
Yeah. So I'm I'm not good at the mathematics and I cannot really understand the um, formula, but I'm I want to ask, so is this VACC is a ventral anti-cigarette cortex?
Yes, yes,
Uh-huh.
yes.
Why did you choose this VACC?
Okay. Yeah. So this is a very good question. So, essentially is we do so because I'm working on the mathematical modeling, and once we build
Mm-hmm.
the model, we need to test this model. So one way to test this model is based on the computer simulation, right? And in
Yeah.
computer simulation, one way is you need to use some kind of biophysically possible model instead of a deep neural network, because yeah, so that's the starting point. And actually here, based on my research, I think there are two models that people has been widely used. So one is the Parkinson's model developed in,
Mm-hmm.
I think in like uh Duke University by Warren Grills.
Mm-hmm.
Yeah. So the other is for the is for the major depression. They have this kind of computational modeling, and yeah, that's what they built as a model. So I didn't build the model. That's what they built the model, and they try to model they call it reciprocal
Mm-hmm.
interactions between the VACC and I think the DRPFZ is the dorsal prefrontal cortex. So they have some
Yeah.
reciprocal interactions. And thanks to their model, they have some kind of it's very tiny, it's very small. So they have like a small IDBS terms here. So which means you first is you can define what's the output you want, and I define this output because I saw that in their paper in the healthy people that they usually have like a very like they have like a like higher like a theta band for the DLPFC
Mhm.
and the lower like a band power for the kind of like a basically for the VACC for the high gamma, high beta, and like a high power, high frequency band. Yeah, so that's what I
Mhm.
define. I mean, it's not that's kind of mathematically sound, but I mean in practical, this kind of numbers is something like this can be like a varied, right? There's no need to be like a stairs function. We make it to be a stairs function. It's because we simulate something more. We try to consider something like, for example, like the people's behavior. They may change like periodically. For example, during the like a night or like a daytime or nighttime, or based on some kind of regular movement, and we want to see whether your model can try to regulate some of the, at least as a brain signal, to some kind of level that you reasonable level that you can try to safely control it. Yeah, that's the main goal. Yeah.
Mhm. Okay. Yeah. Thank you. Thank you.
Yeah, and I think one thing I can say another thing that I can add on is, um, I think right now, currently, people are mainly, I think the state of the art method people has been applied is this responsive DBS. They call it responsive DBS, but basically it's just on-off controller. They do some kind of clinical trials. I think they publish a lot of like Nature papers, Nature Biotechnology or Nature Biomedical Engineering, but like Nature Neurotechnology papers about the responsible DBS for the treatment of some brain disease. And yeah, it seems scales very well, uh, but it's only limited to some kind of well-known disease. So not many research works has been applied this kind of DBS or the neuromodulation technology to test on a very wide range of brain disease, brain disorders. Yeah. Yeah, so we will see how it really works, how it scales for some different disease. Yeah.
So that means you need to recruit more people and more patient in the clinic or like a hospital.
Yeah, that's for one thing. I think that's for the ultimate thing. I think the next step is if we want to see whether this algorithm can work. First is at least we need more computational models of this brain
Mhm.
disease, right? That would be more safe way to do that. Right, because different brain diseases, they are like describe differential equations or some kind of simulate platforms. They are different, and so sometimes okay, this one is a general framework, and this is very like mathematically sound, I can say. But some kind of brain disease is not that important. For example, I think in epilepsy, from what I know for the epilepsy, um, there's no need. I can say there's no need to build a state space model for that. The epilepsy is as long as you can predict when the epilepsy happens, just 10 milliseconds before. Even don't need to be longer, just 10 milliseconds before the epilepsy happens, you give a pulse trend, and you can do
Mhm.
it very well. Which means it's purely become a brain decoding problem instead of like closed loop system. But some kind of brain disease, for example, like a Parkinson's disease, I observed there indeed has some brain dynamics, underlying brain dynamics, which you need to model if you really want to achieve a very good control performance. So it really depends on the disease. Yeah,
Mhm.
yeah. Because ultimately, I want to approach the BCI as a closed loop BCI is for the real applications. If the application doesn't require system modeling, there's no need. Then we can do the decoding very well. Like once we can do the decoding very well, we can do the prediction very well. That's enough. Yeah,
Mhm.
yeah.
Okay, so that means yeah, like the research should be like a step going the little by little and step by step to
Yeah.
make the validate your model, and after that the applying for the many like a disease or something like that.
Yes.
Hmm.
Yes.
Okay, thank you.
Yeah. Any other questions? Or maybe we can visit the lab. Yeah, if no other questions, I think maybe we will start from here. And just as CJ mentioned, so this kind of seminar will resume at 3.
Yeah.
Yeah. Okay, cool.